Okay, we're going to do a example calculation for calculating the bolt and member stiffness of a bolted joint. We've got a model here of kind of what we're going to do. So we're going to have a top plate, a bottom plate. This model is demonstrating the frusta that are in the clamped region of the bolted plates. So this is just showing the region that we're going to calculate the spring constant for of the plates themselves. It should also be noted that since these washers are in the grip of the bolt, so there's the nut, well, there's the nut and there's the head. They too are part of this frusta. I just didn't really create the model that way, so this is sort of generalized. So what we're going to do, let's talk about the dimensions of what we're going to model. And then let's go over to Mathcad and build this mathematical model to calculate this stiffness. So I'm going to use a bolt like this one where there's an unthreaded region and a threaded region. Obviously this one's too long for this. What we're going to use is an M10 by 1.5 and it's going to need to be long enough to go through the washer, plate 1, plate 2, the washer on the back side, the nut, and then extend a little bit past the nut, 2 or 3 threads past the nut. So if we just measure that total distance, it's going to have to be in the total length is going to have to be about 60 millimeters. So it'll be a 60 millimeter long fastener with a few millimeters of threads past the nut. If you didn't have the physical things to measure, like we can go and measure this, then there are charts that show you the thickness of the various nuts. You can have thin or regular or oversized, so you can have different styles of nuts here that you can calculate, go look up the actual dimensions for. Same thing for washers. So you could go look up all of those dimensions if you wanted to. We just have it here, so we're just going to measure it. The plates are going to be 20 millimeters thick each. And these are thick, oversized washers. I don't know if you can see them too well, but most washers are not nearly that thick. But for demo purposes, here's a big washer here, and it's not that thick at all, an actual real one. But this is 5 millimeters of washer, way more than you normally have, but that's what we're going to go with. And so 50 millimeter thick washers. We're going to go with the washers are both going to be steel, and plate 1 up here, the top plate, kind of get some separation there. The top plate is going to be steel, and we'll make the bottom plate aluminum so that we can see how it affects having different materials. So there is one little shortcut that we could take that I'm not going to take just for the purposes of being a little more thorough on how we're going to do this. But since the steel washer on the top and the steel plate, those could be treated as one group. They're both steel, so they have the same modulus of elasticity, and they're touching one another, so they could be part of, in this case, this blue frustum up here. Frusta is the plural. So they could be collapsed together into one thing of a thickness of 25 millimeters. So we could do that. I'm not going to, just so that we can do one particular little calculation on how you get some of these dimensions when you can't do that. Like when they're steel and aluminum, you can't mix those together because they're different materials. Okay, let's go to Mathcad and calculate. First, let's do the bolt stiffness. And here we've got equation. Let me look up the actual equation number so you can reference it. This is in Shigley 10th edition. The equation number that we're going to be using is 817, so we'll write that down. There we go. Well, that's going to actually do math, isn't it? We want to not do math right there. We just want equation 817. In 10th edition, that's on page 419. Okay. This equation is going to need the area of the threaded region, there's actually a couple of things we need to calculate, because the bolt that's actually in here is the printed one that's in here is fully threaded, but we're going to model a bolt that has a unthreaded portion and a threaded portion, so that it's more like this, just shorter. And so to do that, we know the total length of the bolt is 60 millimeters. We just measured how far it needed to be. Again, these don't come in easily. They don't come in 62.28 millimeters, so you have to round out to the nearest larger size. So if this thing actually measured to need to be 58 millimeters, there's probably not going to be a 58 millimeter bolt that's easy to find, so you round up to 60 millimeters, or the next round size. And again, in the back of your book on page 1043, there's a table, I think it's A17, I don't remember the number, I think that's it, that has lists of common sizes for various things. And 60 millimeters, that is a common size. So first, let's take and get some of these links of the threaded versus unthreaded regions. So let's skip equation 817 for a little bit. And L, the total length of the bolt, not including the head of the bolt, is 60 millimeters. Okay? And again, this is for an M10 by 1.5. So 10 millimeter diameter, I guess we can put that in. D, lowercase d, is going to be 10 millimeters. We have the length of the threaded portion and the length of the unthreaded portion. So there is it's not a numbered equation, but it's on page 418. I'll show it in the book here. Let's move our samples out of the way. And it's right over here are a set of equations. So they're kind of crooked, but they're down here. They have the length of the threaded region, and they're based on piecewise functions for either inch. We're in the metric series, so ours is 2d, so 2 times the diameter, plus 6 millimeters for a bolt that is both less than 48 millimeters in diameter and 125 millimeters in length. Our bolt fits into that category. So this calculation will give us the length of the threaded portion of the bolt, not the threaded portion in the grip necessarily, but the threaded portion of the bolt. So that's going to be L, and it's a capital T here for this, kind of to distinguish that it's not necessarily the part that's threaded and in the grip, it's just the threaded part of the bolt. And the equation was 2 times the diameter of the bolt plus 6 millimeters. So 26 millimeters. So if that is the length of the threaded portion of the bolt, then here we can have, and they use LD, lowercase l. So the lowercase l's are talking about the part in the grip. The uppercase l's are just talking about the bolt as a whole. So LD, this is the unthreaded portion of the bolt that is in the grip. All of the unthreaded portion should be in the grip. You can't really create the clamping force if it doesn't have threads. So all of the unthreaded is in the grip. So LD would equal the total length of the bolt, which is just L, minus the length of the threaded part of the whole bolt, this number. So 34 millimeters. And so now, we didn't ever actually write it down, but L is the grip. For our setup, everything in the grip is washer, top plate, bottom plate, another washer. I said the washers were 5 millimeters and the plates were 20, so that's a total of 50 millimeters in the grip. Whoops, wrong thing. So L, lowercase l, the grip is 50 millimeters. Okay, keep moving this guy down. I guess I should have moved it really far down. Now we've got the length of the threaded portion. Well, we have the length of the threaded portion of the entire bolt. We need the length of the threaded portion in the grip. So we have the grip. So let's do length of threaded portion. Again, lowercase, meaning that it's in the grip, is equal to the length of the grip minus the length of the unthreaded portion, which is also in the grip. So 16 millimeters of threaded portion in there. Okay, a couple of other things we need. We need the area of the unthreaded portion. So that is just going to be pi times the diameter of the bolt squared over 4. So just the area of a circle. I've created it as a function. I don't want that. There we go. Let's put it in millimeters since we have everything else in millimeters. We need the area of the threaded portion. So this is not quite a calculation. This is a number that we're going to look up in the chart. And for our M10 by 1.5, I'm looking on table 8.1 over here. See if we can kind of show it quick. Table 8.1 over here. We're looking at an M10 1.5 tensile area, 58 millimeters squared. Okay, so I don't need that to come up. 58, we're just going to type that in, millimeters squared. All right, at this point, I believe we have all of the things. Well, no, one more thing. We need the modulus of elasticity. This is going to be a steel bolt. Modulus of elasticity 200 gigapascals. If you watch the video before this one, where I was doing this kind of live, I put megapascals and the numbers just weren't coming out where I thought they should. It was because it should be gigapascals for steel modulus of elasticity. All right. And the units came out a little bit odd. I'm sure that'll happen here, but we can fix it. It's just the way they displayed it. All right, so what we want now is bolt stiffness. So this is actually, now we can bring this guy back up. Equation 817. All of these other equations aren't really numbered, but they are on page 418, I believe. Let me make sure about that. Yes, they're on page 418. So all of the equations up here are either things we looked out of the chart somewhere, like modulus of elasticity, or these type of equations are on page 418. All right, bolt stiffness. Equation 817 is equal to the area of the unthreaded region times the tensile area of the bolt, so that's in the threads, which we looked up out of the chart, times, I believe, E, modulus of elasticity. All of that divided by the area of the unthreaded times the length of the threaded, plus the area of the threaded, so the tensile area, experimentally determined, times the length, let me move the cursor, length of the unthreaded. And it defaults to these kilograms over second squared. We can just change those to newtons per meter. And now we get numbers much more in line with what I was thinking. This should be a pretty high number. This is the spring constant, saying how many newtons does it take to stretch this spring or compress this spring, which is a bolt, a meter. So it should be a large number. Now, you probably can't actually stretch the bolt a meter and still have it intact, but were you able to do that, this would be the amount of force you'd need to do. All right, that's the relatively easy part. Now, we need to deal with these parts, these frusta. So it would probably help if we draw out what's going on here so that we can kind of draw these onto our diagram. So we've got the bolt head. The bolt head is not part of the grip, so we don't really have to include it in anything. But then we have this washer down here. And again, I made a really thick washer, kind of just so it's visible. But this is the washer. There's the top of plate 1. There's the bottom of plate 1, which is also going to be the top of plate 2. There's plate 2. And again, we're making this steel. We're also making this steel. And the bolt is steel. And then we've got our bolt going through here. This is an M10, so this is a 10 millimeter hole and bolt that we're assuming. Then we've got another washer, steel washer. We're going to make this second plate, though, we're going to make it aluminum, so that we have a different material here. If this was all steel, we could use one of the shortcut equations, even the one that has a curve fit to it, so it's a really simple equation. Then we've got the nut. Nut is not part of the grip, so I'm going to draw it though. And then there should be a couple of threads past the nut. So this is what we're dealing with. So hopefully that's not too light and you can see what's going on there. Let's see. I have the frusta. I have blue on top. So let's get a blue. I guess this was blue. So technically, this is going to start under the bolt head. So it's going to start under the bolt head, and this is a 30-degree angle. So that angle is going to be 30 degrees. And it'll do the same thing on the other side. And it's going to have this slope until it gets to the center of the grip. No matter where this line is, where the two plates meet, it's the center of the grip. So in this case, we have a symmetric one. We'll do another one in another video where it's not symmetric, because that is a slightly more complicated situation. But we'll do one of the calculations that you need for that in here. Once it gets to the center of the grip, then it becomes a mirror image. So something like that. So what we need here is we're going to actually do 4 different regions. So we'll do this region here, which will be an exact copy of this region. These will be identical. They're the same geometry. They're the same material. They're just mirror images of one another, which doesn't change their spring rate. It just they're just mirror images. So these two will actually be the same exact thing. Then we'll also do this region. This region here could be combined with the one that I kind of colored orange up there, because they're both steel, steel washer, steel plate, and they're touching one another. So those could be combined into one region, so that would give us one less equation to do. Since we're using Mathcad, it's just kind of cut and paste, so there's a reason I want to keep them separate so that we can figure out how to calculate this top part. And then this region will be our 4th one. We can't combine this region with this orange one because we would be combining aluminum and steel. So those can't be combined. And it's a different, it's not just a copy, a mirror image of this one, because it's a different material. So we can't just use this one's value and, you know, treat it like the mirror image because it's a different material. All right, so let's do this steel washer first. So the equation we're going to use, we're just going to use the generic equation, which is, let me look it up, equation 820. So let's go back to Mathcad. And that's on page 421. All right. Now this equation is sort of lengthy. I think I'm going to copy it and see if I can paste it over here. All right. Now it's got some stuff that we haven't defined yet, but we'll do that in a second. All right, so it wants to know, this is the washer. So we're doing the washer. Technically, we could be doing either one of these washers because they're both the same geometry, same material. But I'm thinking of this as the top washer. The thickness of the washer is, we defined it to be, or created it to be 5 millimeters. So we have that. This uppercase D. This is the start. Let's look at the picture here. It's basically this dimension here. It's the start of the smaller edge of your frustum. And I drew it, and it looks a lot like it's the bolt head diameter, which it may end up being that, but how we're going to treat it is this one, when we're dealing with a washer anyway, and it's in the top of the clamp region, the grip, we're going to treat this top as 1.5 times the diameter of the hole, which in our case is 10 millimeters, because we're creating the hole and the bolt as the same. Technically the hole is probably a tiny bit larger than 10 millimeters, but we're going to go with 10 millimeters. So that's going to be how we define uppercase D. Well, no, it's 1.5 times D. I wrote that wrong. So it's actually 15 millimeters because our diameter is 10 millimeters. Okay. Lowercase d is always going to be the hole through the middle. So if we take these apart, you know, no matter where we're talking about, the hole is the same size in the frusta. So it's always 10 millimeters, or it's always the diameter of the hole, which in our case is 10 millimeters. Okay, let's go back here. What else? So we need E. We already have E, but I'm going to create it here again. We have it from our bolt, which was also steel, but just in case. All right, so we get a, you know, a pretty large stiffness here. This would be just the stiffness of this washer. So that's all this is. It's just this one. Now again, we could combine this steel washer with this steel plate if we wanted to, since they are both steel and touching. So we could do that, and they're going the same direction. It's not like it's one is going with a negative slope and one's with a positive slope. So we can combine those if we wanted to, but I do want to create this one separately for this purpose. So let's go back to Mathcad, and basically let's copy all of this stuff and paste it. Now let's change it to plate, or top plate. The thickness, we don't need the washer thickness anymore. The top plate is, and the bottom plate are both 20 millimeters, but we're going to create this. We need to change the thickness here to the top plate. Also here. Well, that's not what I wanted. There we go. E can stay at 200 because it is steel. D is, like I said, that's the hole through the middle of it, so that's still 10 millimeters. But this one is no longer 1.5 times the diameter, because now what we have is, and we might have to go here, this that we're talking about is this distance. So this is why I wanted to keep them separate, was to calculate what this distance is. And we could have just done it down here, but I want to do it here. So what we have to do here is we have to think about what this distance is. So let's draw a center line. So that would be this center line right here. There's the edge of the hole, which this distance we know is 5 millimeters because the hole is 10 millimeters in diameter, so that's 5 millimeters. And then there is this piece right here. So from here to here, this piece, and then we go down with our 30-degree, you know, something like this. And we want to know that distance. So to get this distance, we actually need to go to the washer and do a similar thing. So center line. The washer is like this. Again, we have 5 millimeters, but in this case we actually know this distance. Remember the diameter for the top of the washer frustum was 1.5 times D. So this whole length from here to our center line is 7.5 millimeters, half of 15. So this is 2.5 millimeters. So I guess I could have just written this whole thing as 7.5 if I wanted to. And then we've got this tiny little triangle right here. So let's enlarge that triangle to make it more usable. This height of the triangle is the height of the washer, you know, the thickness of the washer, which we define to be 5 millimeters. This angle is 30 degrees, and I want to know, I already used X, so we'll use Y there. I want to know Y. So I've got a tangent situation. Tangent 30 degrees equals the opposite side, Y, over the adjacent side, 5 millimeters. Therefore, Y equals tangent of 30 times 5, whatever that number is, 2 point something. Let's see. Tangent 30 times 5, 2.89. And that is this little distance right there. So the top of our entire, you know, this is only half of it here, so it would be 7.5 plus 2.89 would be this distance. So let's see what that is. 7.5 plus 2.89, 10.39. And D, the uppercase D, would be twice that because we actually want from here to the side over here. So we want actually that distance. So just twice of the 10.39. All right, let's go back to Mathcad and put that in. So D is no longer this equation. Let's move this out. Ah, come on. Can't grab it. All right, what D will equal, there's two of these, so 2 times, how I'm going to write it may not be the most efficient way, but it's what I'm going to do. 1/2 of 1.5 times D. So this is basically the 7.5 that we had before, plus the tangent of alpha times the height of the washer, thickness of the washer, which you have as a variable. I'm doing this so that I could change all of these thicknesses and diameters, and it would, I don't have anything hard coded in other than the 1.5. So we should be able to do equals, except that we haven't defined alpha. So it's got something built in for alpha, but it's not what we want. Alpha is equal to 30 degrees. And there's our 20.77, which is twice the 10.39, more or less. I guess it rounded a little different somewhere. Okay. And we also, by doing that, calculating that correct number, we calculated our stiffness for our blue shaded steel piece. The aluminum has the exact same geometry. So I can copy all of this and create a new page, paste it in. The only difference is going to be that it's made of aluminum. So instead of 200 gigapascals, it's like 70 gigapascals. Everything else, it has the same dimension here. Let's make sure. So you don't use the larger one. You know, you might think that you're working your way down here, but the way this equation works, that capital D is the smaller diameter of the frusta or frustum. So it's the same as what we had here. You don't use the larger diameter, it's the smaller one. The angle of 30 degrees kind of the angle of 30 degrees combined with the thickness in the equation embeds the larger diameter. So you wouldn't use this as D. If you use this as D, then it would create a frustum that went, out like this, which is not what we want. All right, back to Mathcad. So we did get still a large number, but smaller than we had before because of our smaller modulus of elasticity. All the other dimensions are the same. The last piece is the washer on the bottom, which is exactly the same. They're both steel, and they both have the exact same geometry, so I'm not even going to put that in as another equation. So I've got the spring constant for the washer, spring constant for the steel top plate, and the spring constant for the aluminum bottom plate. To combine all of those together and get the stiffness of the member, they are all springs in series. They're all stacked on top of one another. So springs in series add as the reciprocal. So Km would be 1 over K of the washer plus 1 over K of, I called it the top plate. Oh, I just noticed I didn't rename the plate here. Let's change this from top plate to bottom plate. And change this. There we go. So that plus 1 over the stiffness of the bottom plate, and then we have a washer, which I could have done 2 times the other one, but plus 1 over stiffness of washer. All of that equals, and then we get our weird units, so let's do newtons per meter. A 1.07 times 10 to the 9th newtons per meter for the member stiffness. So with this member stiffness combined with this bolt stiffness, we can then move to the next part of figuring out how much of an external load. So all of this stiffness is created by clamping down the bolt, tightening the nut on the bolt and clamping this joint down. And then on top of that, we probably want to have some force that is trying to pull our 2 plates apart, trying to pull them apart. And now that we have these 2 stiffness numbers, we can start to figure out how much of that external force is relieving the compression in the plates versus adding more tension to the bolts, and at what point do the plates separate and now our joint has failed. Usually joint separation is a failure because at that point the bolt is taking all of the load by itself, and you have a gap here. Maybe you didn't need a gap. Maybe something escaped through that gap, or who knows. But joint separation probably means that joint has failed. All right. We'll do another of these examples later, but I think this will get us far enough along for working through all the little bits of how a joint and member, a member and a bolt stiffness can be calculated. See y'all next time.